In this video, we're going to talk about how to use sample spaces and tree diagrams. A sample space is the set of all equally likely possible outcomes of an experiment. Let's look at an example. We want to list the sample space for flipping 3 coins. So when we flip 3 coins, the outcomes that we care about are whether or not the coins are landing on heads or tails. So one possible outcome is we could have all 3 coins land on heads. Another outcome, we could have 1 land on heads and 2 land on tails, but we have 3 different coins, so any one of the 3 could land on heads. We could also have 2 of them land on heads and 1 of them land on tails, so we could just flip around the order of the H's and the T's. And then the last thing that could happen is we could have all 3 coins land on tails. All of these possible outcomes would make up our sample space for flipping 3 coins, and in here we see that we have 8 equally likely possible outcomes. Listing a sample space is a useful technique for solving some probability problems, because if they ask you the probability of a particular thing happening, and we have our sample space listed, you can see how many possible outcomes that is and what the total number of possible outcomes is, and then use that to find the probability. Let's look at some more examples. We'll list the sample space for rolling 1 die. Assuming it's a regular die with 6 sides, it would just be 1, 2, 3, 4, 5, 6. We will see problems where there are some dice that are labeled differently or have more or fewer sides than 6, but if you're just told in a problem that there's 1 die or 2 dice and you're not given any additional information, just assume the regular dice. And again, here we have 6 equally likely possible outcomes. Now we want to list the sample space for rolling 2 dice. This is a little bit more complicated because we have to take into account what number is on the first die and what number is on the second die. And if we do this carefully, we can keep things organized and keep track of our possible outcomes. So first we'll look at the case where we land a 1 on the first die and 1 on the second die. If we land 1 on the first die again, we could roll a 2 on the second die. We could roll 1 the first time and 3 the second time, and so on. So everything that we have written here, these are all of the possible ways to roll 2 dice where the first die lands on the number 1, and then the other die could land on 1, 2, 3, 4, 5, or 6. And now we're going to repeat this again, but we're going to assume the first die lands on 2. And then the second die would land on 1, first die lands on 2, second die lands on 2, and so on. Here we have 36 equally likely possible outcomes, and this is everything that can happen when we roll 2 dice. This is also the same sample space for if we had rolled 1 die 2 times. Just remember, this is the number on the first die, and this is the second number is the number on the second die. Now let's look at another example where we can make use of the sample space that we had in the last problem, or a similar sample space. Here we're asked, when a die with faces marked 1, 2, 3, 4, 5, 7 is rolled twice, find the probability that some different things happen. Now, this die is not a normal 6-sided die. It does have 6 sides, but instead of the number 6 on one of the faces, we have the number 7. So the easiest way to solve this type of problem would be to list out the sample space. It's going to be similar to what we did in the last example, where we listed out the sample space like this for rolling 2 regular dice. Here the only difference is we're rolling a dice that's marked differently 2 times, but we'll use the same technique to generate the sample space. Then once we have our sample space generated, we'll look more closely at what probabilities they're asking us to find and see how we can find them in our sample space. So our first die could be 1, second die 1, 1 and then 2, 1, 3, 1, 4, 1, 5, and 1, 7. So we don't have a 1, 6 here because there isn't a 6 on this die. Then we would generate the rest of the sample space pretty much the same way, except everywhere there was a 6 before, we're going to write a 7 because this die doesn't have a 6 on it. So here we've listed our sample space for everything that can possibly happen when we roll a die with these faces 2 times. where the first number would be what we get on the first roll, and the second number would be what we get on the second roll. Part A is asking us to find the probability that both rolls are even. What we'll do here now is look at our sample space for every instance where an even number is rolled twice. So 2, 2 would be 1, 2, 4, that's it, 4, 2, 4, 4, and that's it. We only have 4 possible outcomes where both times an even number is rolled. So here we would say this is 4 out of 36, and again that's because in here we have 36 equally likely possible outcomes. And 4 of them happen to be ones where both rolls are even. Now for part B, we want to find the probability that the sum of the rolls is greater than or equal to 10. So that means when we add the number on the first roll and the second roll together, we want them to be 10 or a number that's larger than 10. So for looking for this, it's a little bit tricky, but our larger numbers tend to be towards the lower right. So we would want to add up numbers here to see which of these have a sum that's equal to 10 or greater than 10. So 7 and 7 add up to 14. 5 and 7 and 7 and 5 add up to 12. Then 4 and 7 and 7 and 4 add up to 11. So that's going to hit this line. And we have 3 and 7, 5 and 5, and 7 and 3 add up to 10. 2 and 7 add to 9. 3 and 5 add to 8. 4 and 5 add to 9. 9, 7 and 2 add up to 9. So all of the possibilities here that we've drawn red lines through have a sum of 10 or greater than 10. So if we count all of these up, we see that we have 8 out of 36 possibilities. And now one thing that I'll mention is if we had been asked this problem with regular dice instead of these weird dice, if you list your sample space out like this, it's actually very easy to see what the sums of all of the rolls on dice are. Like here, 1 and 1 is 2, 2 and 1, 1 and 2 adds up to 3, 1 and 3, 2 and 2, 3 and 1 add up to 4, and we can just keep following diagonals like this to see what the sums of the rolls are, but it only works out nicely like this if you're working with regular dice. If you're working with dice that have some modifications to them, or some of the sides are different, you can still kind of follow this like we did in that example, but it's not always going to work out quite as nicely as this. So 4 and 6, 5 and 5, 6 and 4 add up to 10. 5 and 6, 6 and 5 add up to 11. And 6 and 6 add up to 12. So it works out really nice if you're asked about normal dice. If you're asked about weird dice, not as nice, but it's still doable. Part C is now asking us to find the probability that the second roll is exactly 3 more than the first roll. So if our first roll is A, we want our second roll to be A plus 3. We could try looking for some of these in here, but it might be a little bit easier to list out our possibilities and then search for them inside the sample space. So we could roll 1 first, and then we would want to roll 1 plus 3, which is 4. We could roll 2 and 5, because 5 is 3 more than 2. 3 and 6 would be possible, but we don't have 6 on this roll, so we're going to eliminate that. And then we could roll 4 and 7, because 7 is 3 more than 4. So these are the 3 different outcomes that work, and now we can search for those in the sample space, and yes, we just have these 3 possible outcomes out of 36 total equally likely possible outcomes.